Thank you for that introduction, Kathy, and thank you all for being here today. It's overwhelming to see everybody show up for you, but I appreciate it, and I really appreciate the support. Okay, let's do this. So as Kathy said, today we'll be talking about my research that I have done as part of the Odom School of Ecology and Integrative Conservation Program. This represents work that I've been working on for the past 6.5 years, so it's going to take a while, but here we go. So I work on issues dealing with freshwater management, and freshwater can be difficult to manage because it's limited in supply and it can be hard to predict availability through space and time. And we know that these issues are worldwide. There's only so much water available in the world, and it's hard to predict through space and time. For example, this also occurs in Texas, which is my home state. I have these pictures taken by my dad, who is here today. This is from our new backyard. This is a reservoir, Lake Travis in Austin, Texas. You can see this picture is from August 2018, and this one is from October 2018. And I've added a line so you can see the shore, seeing how much water has varied in a very short amount of time. There's also a slide for scale. So we know that this is probably an issue if you're thinking about how to manage fresh water when it's so variable in just a few months at a time. We also know that these freshwater systems support a lot of different life and processes. So first, talking about ecological systems, we can see on the left in this top part, we have a shrimp community that exists in Puerto Rico. We have 2 different species of shrimp that rely on water found within streams. We also know that streams support important processes like sediment transport. So this sediment is coming from mountainous areas where the headwaters begin and supplementing these coastal beaches that have lost sand due to erosion. And then also there's evidence that streams actually act as a carbon sink, so they're able to hold on to carbon dioxide from the atmosphere. So all of these important stream processes that occur in the ecological area rely on some amount of water being present in the streams. We also know that in terms of social systems, a lot of these other important services we rely on also require a certain amount of water that originates from streams. So we interact with water in our daily lives. People drink it. We need fresh water to drink. Also, some people use hydropower that is generated by streams. So this is a dam in Puerto Rico that's a hydropower dam. And then finally, it also can be a source of recreation. So this is in Puerto Rico. Streams are very important in terms of recreation activities for people on the island. And again, these all rely on a certain amount of water being available in the stream. So given that water is limited and it's getting harder to predict through time, managers are struggling to be able to meet ecological and social needs for fresh water in streams. Now, because I'm in the Integrative Conservation Program, I get to think about my question from a social perspective as well. And a water system is a great place to do this because it's coupled. It's a social ecological system. So we have this water originating in streams. It's being removed from streams by intakes. It goes to a treatment center, and then it comes out in people's houses through the tap. So this represents a coupled social ecological system. And because this is coupled, we know that feedbacks within the ecological system affects the social system. And then again, what happens in the social system circles back to the ecological system. So thinking about how can effects in one area affect the other. And so that brings me to my main overall question for today, is how can trade-offs between ecological and social needs be better balanced when we know that these are connected? Now, as I mentioned, this issue exists worldwide. You could look at this question anywhere. How do we balance the social and ecological freshwater needs? But I am focused in Puerto Rico. So why Puerto Rico? Well, one reason is that these ecological systems are very diverse and full of many migratory species. So we have a wide range of different species represented here. At the top, we have American eel. Here we have mountain mullet, the goby, freshwater shrimp, and this is actually 2 different kinds of shrimp. This is an adult shrimp. Here, these are actually juvenile shrimp that are crawling back up the stream, and you can see their little eyes represent the individuals, so they can be very tiny. And then we also have these snails, and all of these have to migrate between the ocean and streams in order to complete their life cycle. So these streams are supporting this very diverse migratory species community. We also know that those diverse species are providing important ecosystem services for the streams. Specifically, we've seen there a lot of work done on the importance of having shrimp in a stream. So if you have a pool such as this, which doesn't have any shrimp, you can't even really see the bottom of the stream. This is covered in algae and sediment. But if you add shrimp and wait a few days, you can actually see the shrimp have cleared off the sediment, removed the algae. So they're an important part of maintaining water clarity within this system. So that's another reason that Puerto Rico is a great place to think about balancing ecological needs for fresh water. In terms of the social system, we know that Puerto Rico has municipal water supply issues. If you've been paying attention to Puerto Rico in the news, over the last 5 years, we've seen the island lose access to water multiple times within 5 years. One of them was when Maria hit in 2017. This was due to losing power, but we had people on the island not having access to water for multiple months. There was also a major drought that hit the island in 2015. Again, people didn't have access to water. We also know that leaks are an issue as well within the system. So this is a picture of a pipe moving water from streams to a treatment center, and you can see there's a leak here. So all of these reasons make Puerto Rico a great aspect in terms of a social aspect. We also know that there's a large concentration of intakes on the island. So this is just an inset of El Yunque National Forest, which is located in the northeastern corner of Puerto Rico. From this inset, you can see how much of the island it represents. It's basically covering almost the entire northeast. And this is the outline of the actual forest. El Yunque National Forest is managed by the U.S. Forest Service, and we can see that there are multiple watersheds that make up this boundary. You can also see that each yellow dot represents an intake. So there's a really high density of intakes, and these are all located on streams. So this is another reason that Puerto Rico is a great place to think about these issues. People rely on water that come from streams much more than maybe other places around the world. So for those reasons, I'm thinking about these questions in Puerto Rico, and to give you a little background of what the presentation structure is going to look like, focusing on this main major question, how can trade-offs between riverine connectivity and human water needs be better balanced? I'm going to break this down into 4 smaller questions. And then after I answer these first 3, how does connectivity vary through time? How does water withdrawal affect connectivity? Is water management legislation implemented in practice? We're going to use what we've learned from those 3 sections and answer this final question of how do management actions affect social and ecological resilience? For those of you that are interested, each one of these represents a chapter of my dissertation, if you plan on reading that later. So you can follow along in that way. Okay. Also, again, because I'm in the ICON program, parts of my dissertation are ecological, parts are more social, and then the final question is kind of an integrated look all around, and theoretically. Okay. So, how does connectivity vary through time for freshwater shrimp? And I want to take the time to point out how intakes work in this system in Puerto Rico, if you're not familiar with it. What happens in El Yunque National Forest, which is where this research is based, is you have these small dams that are only 1.5 to 2 meters high. They block enough water to create a pool, and then it submerges this intake within the pool so it can suck water up, and you can see this pipe will then move water down to a treatment center to be treated, and then it will be accessible to domestic users. So when I'm saying intakes, you can think it's usually attached to a barrier, and that's kind of what they look like for reference. Also, as Kathy mentioned, this research has been published already in the River Research and Applications, if you care to read more about it later. Okay, so since we're thinking about connectivity, we need to understand the shrimp life cycle. If you've heard me talk over the past 6.5 years, you probably know this well, but we're going to do it one more time. So the adults start off in the headwater stream. They release larvae, which passively float down to the ocean. The larvae will develop for 50 to 100 days. 50 to 100 days, and then the juveniles will then find a source of fresh water and actually climb back up. And we saw that picture of how they look when they're climbing. So they climb back up, and they can be quite small. This is a picture of me with one of them on my thumb for scale, so they can be pretty tiny. The juveniles will then live out their life as adults up in the headwater streams. Oh, and these shrimp can get to be quite large. This is a picture of a shrimp, half of a shrimp with my finger for scale. So you can see that they can be fairly large for some of these species. So looking at it this way, we can see that moving from the headwaters down to the ocean and back connectivity is important. This connection from the ocean to the headwaters is necessary for these shrimp to be able to persist. And so if we start thinking about what can affect that connectivity, that's where these intakes and barriers can come into play. So on the left, we see an example of high connectivity. So this would be an example where we have no dams, no intake. All of the water is able to move down to the ocean. That's an example of high connectivity. But if we look here on the right, we can see that connectivity can be lowered if you have an intake that's paired with a dam. So you're removing some of that water, and that's decreasing the amount that goes to the ocean. For us, that represents a loss of connectivity for shrimp. The more water you remove from this system, the less connectivity there is. So that's how we're thinking about connectivity here. So again, connectivity is important for these populations to exist. And these populations, we know that shrimp populations are spatially structured around the island. So what that means is that we've had a researcher, Cook in 2010, who collaborated with our lab, went around and sampled different shrimp populations around the island and found that there's no genetic distinction between these different populations. So they're connected genetically. So what that means is that larvae that's released from shrimp up here in Espiritu Santo could float down and colonize habitat in Rio Cuomo. So there's no distinction. So we know that larvae from this system are important to support all these different populations. Also, if we look at the connectivity literature, we've seen that barriers without passage can sever connectivity. And so what that means is if that there's a barrier and there's no water moving over the barrier, then connectivity is lost. So this is being explained to us by this graph where on the x-axis we have year, and on the y-axis we have connectivity. A value of 100 means that the system is completely connected. But what you can see is through time, more and more barriers have come online, and so we're losing connectivity as more barriers come on. So these are complete barriers, and they're totally severing the ability of shrimp to move either downstream or upstream. The system wasn't looking at shrimp, but it's not allowing whatever animal to move up or downstream. So the question is, though, in my system, we have a lot of barriers that are fairly small. That doesn't do that to connectivity. There still is some passage that's probable. We have Kyle McKay, who's on my committee, illustrating how tall these intakes can be.
So pretty short.
They're pretty short. Pretty short. You see how short they are. And so next to him, we can see that water is moving, so that indicates that connectivity exists. However, if we look on the right, now we're looking at an intake looking downstream, and you can see that there's no water below. So these barriers, although they do allow partial passage, there are times where the system can be completely disconnected by these barriers. So the question I was interested in is whether multiple barriers, because we know that there can be multiple barriers within a stream system, can these actually decrease connectivity? So specifically, the questions that I'm asking for this section is, has total habitat connectivity for shrimp declined as intakes were added over 37 years across 7 watersheds in El Yunque National Forest? And we had an idea also of asking whether this decrease in total habitat connectivity is a result of increased withdrawal rates. So are we removing more water from the system, drought, dry season, or water intake location? And just to be clear, the total, when I say total habitat connectivity, I'm talking about the proportion of stream habitat connected to the island-wide metapopulation. So this is looking over all of the habitat within the stream, within the 7 watersheds, how much of that is connected at any one time. So just to take a look at my study site, these are the 7 watersheds that I focused on. You can see it's, again, this is, the boundary is El Yunque National Forest, so we covered a lot of the forest. The black dots represent intakes, so a pretty high concentration of intakes located within this area. And I also, again, want to emphasize that when I'm talking about total habitat connectivity, it's across all of these different rivers that we see located here. So going over how I calculated habitat connectivity, I'm going to first talk about the connectivity index, and then we're going to add the habitat part. So when we think about connectivity index, it's a probability that a shrimp can move from above or upstream of an intake down to the ocean and then back upstream of the intake. So it's a probability of movement. And if I have a shrimp that's above intake 1, for example, it's a probability that a shrimp can move over intake 1, intake 2, down to the ocean, and then back over these 2 intakes. So just the probability of downstream passage times the probability of upstream passage gives us a connectivity index. Now to get an idea of how much habitat is available above these intakes, I then calculated how much habitat was above each individual intake. So if we multiply connectivity index at one intake times the amount of stream habitat upstream, that gives us idea of habitat connectivity for each individual intake. So I calculated a connectivity index for each intake, determined how much habitat was upstream of each intake, multiplied them, and then I summed all of that across all the intakes and all 7 watersheds, and then divided by the total habitat across all the 7 watersheds. And so this gives me an idea of how much habitat is connected within my system. So next, the values you're going to see represent this habitat connectivity index. Okay, so we got a lot of dots. So for a year, again, my time series was 1980 to 2016, and I calculated these values on a monthly time step. So there's 464 dots represented on here. And on the y-axis, I have total habitat connectivity. And for this one, a 1 means that all the habitat is connected, whereas a 0 would be no habitat is connected across all my watersheds. And what we see is that through time, total habitat connectivity tends to be declining. And especially this seems to be true in drought years, so this pink and yellow, habitat connectivity tends to be lower, as well as dry season. So we can see here that the dry season tends to have lower habitat connectivity. And for this time series, we had 2 droughts occur, one in 1993 to 1995, and one in 2015. So when we ran a linear regression on this, we tried to fit 7 different models, and the best fit model had these variables that seemed to be driving this trend that we observed. The proportion of water withdrawn, which is just the total amount of water being withdrawn over a whole system, divided by the total amount of water that would be reaching the ocean. Drought, so whether it was a drought year or not, whether it was a dry season, and then also time. And so time for this, again, we had our moving through time 0 to 464 month period, and we knew that through time there were more intakes being added to the system. So it's kind of a proxy for as more intakes are coming online, how is connectivity changing? And again, here's an up-close picture of what an intake looks like. So one thing to note is that for these 7 models, we knew that proportion of water withdrawn was important, but when we actually plotted it to see how that's changing through time, we see that the proportion of water withdrawn actually isn't increasing. So we would have expected that you're withdrawing more water through time because connectivity is going down, but when we plotted this through time, again over a time series, we see that proportion of water withdrawn is fairly constant. And so that led us to think, well, what is happening? What would be causing that decline in habitat connectivity? And that's where the location of the intake is important. So when we looked at the proportion of habitat negatively affected, which is the habitat that's upstream of an intake, we see that that is increasing through time. So that means later within our time series, they started putting intakes lower down in these watersheds, closer to the ocean. That means that more habitat is upstream of that, and that allows habitat connectivity to decline through time. So it seems that intake location was also important to explain why we're seeing this decline. So in conclusion, we see that total habitat connectivity declined because of proportion water withdrawn, dry season, and drought. But we also see that additional intakes coming online later in the time series is causing this proportion of habitat negatively affected to increase, which is decreasing connectivity. So based on these findings, we suggest it's likely that shrimp larvae has been reduced from over our time series, so less habitat connected, less shrimp larvae reaching the ocean. And from that, we recommend as a management suggestion that different withdrawal rates should be explored in order to enhance habitat connectivity for shrimp, if that is actually a management goal. And just, there's a little surprise in here, even for Cappy. I am a big fan of memes and also communicating science, so I've made a meme for each chapter to sum up what I'm talking about. So this is shrimp not having any water, not being able to climb over the barrier if there's no water.
I like this one.
Yeah, there's 3 more. So Okay, so based on our management recommendation that you should alter the amount of water you're withdrawing if you care about this shrimp habitat connectivity, we wanted to ask, well, how does altering the water rate affect these other organisms that exist in streams? We know that there are other animals that are moving. How does it affect their connectivity? So that's what this chapter is going to explore. So just as a review of our important main characters within our stream system that I'm considering, we have the eel, mullet, snail, goby, and shrimp. And we're thinking about how they're moving through the system. And we know, based on previous literature, that there are different movement constraints for each of these different taxa. So if we're looking at this and we're thinking that this is close to the ocean, you can think about these animals as starting to move up within the river system. How does this community of sibilants change as they go over these different barriers? So if all of these taxa come up to an intake that doesn't have a barrier, we see that everything is still able to continue moving up the river. So everything is able to move as if there's water being withdrawn, but there's no barrier. However, if we reach a 1.5 meter dam, let's see what happens. Is that small enough to allow everything to consider moving? And it still is. 1.5 meters isn't enough to keep any of these animals moving upstream. If you keep moving upstream, however, eventually they may reach a 5 meter waterfall. Now, when this happens, we see that several different taxa drop off. American eel, mountain mullet, and snail are not able to pass over barriers that are 5 meters high. So just all that's left is the goby and the freshwater shrimp. Now when you get to a barrier over 30 meters, which does happen in these systems, there are some very large waterfalls, then above that you would only see the freshwater shrimp. They're the only organism that would be able to climb over that. The goby would also fall off. So knowing that these migratory taxa have different movement constraints, the question became, how do different water withdrawal rates affect habitat connectivity for these 5 different taxa? And ultimately, the goal would be asking if decreasing water withdrawal rates increases the habitat connected for all taxa. We know it's likely that if you remove less water, you'll probably benefit shrimp, but we wanted to ask, is that true for the other 4 taxa that we're interested in our system? So the study system, still working in El Yunque National Forest, but I have limited this analysis to just 4 watersheds. I'm actually only going to be talking about findings from 2 of them because of time. You can see that these different watersheds have different orientations of intakes within the system. So the different management scenarios I looked at are if you didn't withdraw any water, if you could reduce to half the 2016 withdrawal rate, the 2016 withdrawal rate, and then doubling the 2016 withdrawal rate. And if you're curious to know what these different withdrawal rates are, I have them for the cubic feet per second for the different watersheds. And you can see that there are wide variations in the amount of water that's being withdrawn from these systems. So because these are the different scenarios, just know that the water withdrawal rate isn't changing through time. If I'm focusing on the 2016 withdrawal rate, that's going to be constant for my whole time series. And I looked at how connectivity is affected over a 31-year time period on a monthly basis, similar to the first chapter, but a shorter time period. So again, a quick review of how I calculated habitat connected, still using this connectivity index, as I talked about the probability of passage up and downstream, and the amount of habitat upstream of the intake. But now, for some of these taxa, I'm including other variables besides just discharge. So for shrimp, only discharge mattered for their movement, but based on the literature, we know that goby, mountain mullet, and eel are affected by the barrier height that exists within the system. And for snail, they're also affected by height and then just elevation within the watershed. So because all of these taxa have different barrier heights and elevation affecting their movement, this means that each taxa will have a different connectivity index. Each individual taxa has a different index for each intake. So here are the results for 2 of these watersheds. On the x-axis, we have the proportion of water withdrawn. So this represents the 4 different water management scenarios. And the dotted line represents the 2016 water withdrawal rate for reference. And then on the y-axis, we have the watershed habitat connected. So now we're thinking about these watersheds as being separate and individual. So if we focus first on Sabana, we can see that if we take the amount of water that's being withdrawn now and we reduced it by half, we can see that some of these taxa, like the mullet, the snail, goby, and shrimp, are actually increasing in the amount of habitat that's connected. They seem to benefit from removing less water. However, the eel doesn't change in terms of the amount of habitat that's connected. If you look at Fajardo, we can see that it's similar, that those same 4 taxa also see an increase in the amount of habitat that's connected, but the eel, again, doesn't change in the amount of habitat that's connected for that taxa. So it seems that it's beneficial for some of these taxa, but not all of them. And it's important to note that in Fajardo, we see that the eel has the highest amount of habitat connected in 2016. That's because in the Fajardo watershed, this intake doesn't have a barrier. So there's no barrier, just water being removed. And so we can see that reductions in habitat, reductions in the amount of water removing isn't having a big impact on the eel either. But if you look here, if we double the amount of water that you're removing, we do see that eel do respond and actually lose the amount of habitat that's connected. And so that's because of this no barrier. They're more responsive to increases in withdrawal rates if you don't have a barrier present. Whereas in Sabana, if you increase the amount of water withdrawing, again, the eel habitat doesn't change. The amount of habitat connected doesn't change. So in conclusion, if you decrease the amount of water that you're withdrawing, you tend to increase habitat for shrimp, goby, snail, and mullet. However, we don't see that same effect happening on eel in terms of habitat connected. And so our recommendation for management would be to implement a minimum flow at intakes without a barrier to maintain habitat connected for all 5 taxa. Because if you remove more water with no barrier, you actually will have an effect on eel. And we know that these exist within Puerto Rico. Here's a picture of one where this is an intake station, and you can see there's nothing in the stream. So it is possible to do this at some of these intakes without a barrier present. And of course, there's a meme. Little break? Okay. Okay, so given that 2 of those questions, the answer was to implement a minimum flow, implement some sort of regulation to maintain flow, part of my research was to look at whether water management legislation is implemented in practice. And this chapter was done with a lot of input from Laura German in the anthropology department, which has been great to be able to look at this question as an ecologist and learn how to think about these issues. So in terms of implementing a minimum flow, this idea is part of the idea of environmental flows. For those of you not familiar with what environmental flows are, it's the quantity, timing, and quality of water flows required to sustain freshwater ecosystems and the human livelihoods and well-being that depend on these ecosystems. And so minimum flow is only part of this, but in a lot of states that do implement environmental flows, it's what they tend to focus on, that you have to maintain a certain amount of flow in streams at all times. Puerto Rico is no different. There is a minimum flow regulation, but it's the Q99, which is fairly low, and it's the flow exceeded in the river 99% of the time. So this is a regulation that does exist in Puerto Rican legislature, and we can see that this is being implemented in certain circumstances. Here we have a picture of a newer intake that was put in 2005. It's actually been designed to have a constant spillway occurring, so there should be constant water, constant minimum flow being maintained within the system. However, we also know that in Puerto Rico, this doesn't always happen, and if we look to the governance literature, we also know that legislation isn't always necessarily implemented in practice, and there's a lot of reasons for that. One of them can be the misallocation of power and responsibilities within an agency. So perhaps an agency that's responsible for implementing legislation doesn't have the power to do so. Another limitation could be financial. Perhaps an agency that's in charge of maintaining a minimum flow doesn't have the financial responsibilities that make it possible. And then yet another one is that the regulation itself may lack sufficient enforcement mechanisms. So maybe the regulation doesn't outline how this will be enforced if broken. And so again, in Puerto Rico, this is the same picture as before. We can see that there's no flow below this intake, and so no minimum flow is being maintained. So the question became, are there mismatches between environmental flow law, which we can think of as de jure, and then also what we see in practice, which we can think of as de facto? So asking if there are mismatches between these two, and then the second question, looking at whether accountability for state water agencies influence legislation implementation. And so this accountability, there's a lot of literature on accountability specifically, but it can be used as establishing a network of influence. So which actors are influencing others and sort of understanding why agencies are acting the way they are. And so that's why we decided to look specifically at accountability and not some of these other limitations. So for those of you that aren't familiar with social science methods, I'll go over what I did. I was focused on 2 different water management targets within this question. The first one is equitable allocation, which is the principle that every water user has the right to a reasonable amount of water proportional to its needs. And then secondly, water use efficiency, which is the accomplishment of a function, task, process, or result within the minimal amount of water feasible. So looking at these 2 targets in terms of environmental flow governance, because there could be a lot of different things that you could examine in trying to understand this question. The 2 approaches I used to identify these, because I wanted to look at de jure and de facto, is from the de jure, I looked at statutes and regulations and Westlaw. Westlaw is just a database of statutes and regulations, both federal and state. And I used key terms such as allocation, efficiency, and water to be able to make sure that I identified all the statutes and regulations that existed in Puerto Rican law related to these 2 targets. For my de facto approach, I did 15 semi-structured interviews with water managers. These water managers were at the state and federal level. The interviews lasted anywhere from 30 minutes to 2 hours, and some of them were entirely in Spanish. So looking at whether these two targets were met within the de jure and the de facto, and then asking if it exists in the de jure, do we see the exact thing happening within the de facto area? And to identify these 2 targets, we came up with a framework which had multiple questions to be able to identify both of these targets using both of these approaches. So just to give you an overview of what this looks like, we have equitable allocation and water use efficiency. And the idea was that if these are being met in practice and by legislation, then environmental flows would be easier to, or be more likely to be met in terms of management as well, if both of these other 2 targets exist. And we're looking at this by law and then again in practice. So summary of my results for equitable allocation, we see that the Department of Natural and Environmental Resources ensures water is used for the public's benefit, protects water resources for the people of Puerto Rico, intends water use to be equitable, and then prioritizes water for municipal use. So all of these are outlined in the legislation in Puerto Rico. When I talked to managers in practice, I saw that the Department of Natural and Environmental Resources prioritizes water for municipal use. So I was told that the Department of Agriculture in 2012 was pushing to increase water security on the island. They wanted to grow more food locally. Only about 20% of the food on the island is grown in Puerto Rico. So to increase water security, they wanted to start growing more food. But the Department of Natural and Environmental Resources said that all the water was being used for municipal use. And so it was prioritizing the municipal use. And so we did see that happening in practice. In terms of water use efficiency, this one had a couple of different agencies that was involved. So we see the Department of Natural and Environmental Resources decides the best and most reasonable way to use water, and they're also the agency that should ensure water is not wasted on the island. The Puerto Rico Aqueduct and Sewage Authority, which is the water utility company on the island, is in charge of creating regulations to conserve water. And then we also see the Puerto Rican Energy and Power Authority, which is the power company on the island, also should help conserve water resources for the people. And if you're thinking it's funny that the Power Authority is involved with water conservation, it's because the power company operates the hydropower dams. So they do have a role in water use as well. So looking at in practice whether these 3 agencies are actually implementing these different regulations, we see that the Department of Natural and Environmental Resources actually doesn't have criteria for water waste. If you look in the water plan, there doesn't actually state what counts as a water waste on the island. Then we also see that the water utility company is responsible, the actual agency that's responsible for minimizing waste. And so what this means is that specifically in the 2015 drought, it was the water utility company going out and fining domestic users if they were using tap water to clean off their driveways. Also, if they were using it to wash their cars, that was considered a water waste, and they would be fined. But this was just for individual users. We also saw that about 60% of the treated water was not paid for by customers. So this means that the water utility company was removing water from streams, treating it, and then en route to customers, it's being lost. But again, this can't be defined as a waste because the Department of Natural Resources hasn't outlined what counts as a waste. So you could consider it a waste, but it's not considered currently a waste of water on the island. Also, through looking at the different statutes and how these agencies are set up, it seems that the way these state agencies are structured in terms of the law, by law, could also play a role in what we see occurring on the ground. So those three state agencies that are really involved with water use efficiency, we see some similar trends across the agencies. So for example, the Department of Natural and Environmental Resources, we see that the governor appoints the secretary. The secretary oversees the entire agency and the management actions that it takes. We also see that for the water utility company, again, the governor is appointing a majority of the governing board. Everyone that's running this water utility company, it can be appointed by the governor. And then the same thing for the power authority, that the governor appoints a majority of the governing board. So all of these, we see that the governor is appointing them, which can sort of set up a structure for accountability to exist to the governor. Now, when we talk about accountability, you have to be specific how you define it. So for today, we're going to think about accountability as if there are responsibilities that are not being met, then you can have consequences enforced on you. And so thinking about accountability for these state water agencies, if you look at their structure and the governor is in charge of appointing these people, you can ask if there's political accountability. And so that's if people are responding to a political allegiance. And so what we saw talking to people is that the governor was enforcing consequences if responsibilities were not met to the governor. So this was a quote that somebody told me in May. The first Secretary of Department of Natural Resources, PAD, was disobeyed or did not comply with the requirement from the governor, so he was fired. So this shows that there was accountability to the governor. And so we can think that that can have some implications for these agencies trying to carry out different responsibilities that are laid out by law. We can also think that if the governor is responsible for all these different agencies, that can also set up some interesting relations with each other. So how are these agencies supposed to regulate each other if they're all answering to the governor? And so I heard this come across in interviews as well. How is it that the governor would let one of his agencies put another agency head into jail? So how can these agencies enforce different responsibilities if they're all answering to the governor at the end of the day? So what we see is that mismatches between legislation and practice do exist for these different management targets. Also, one thing that comes across is the Department of Natural Resources is responsible for prioritizing municipal water use, but at the same time to maintain a minimum flow. And you can think that in a time where there's not a lot of water, if you're responsible for both of these, how is that going to play out on the ground? So we also see that state agency political accountability may limit implementation of legislation. So this may be something that's getting in the way of these agencies implementing effective legislation. And I want to emphasize that this isn't something that just happens in Puerto Rico. There's been other researchers have looked at the question of politics being involved with water governance, for example, in Georgia. And we do see that politics play a role in determining water allocation issues. So this is an issue that tends to exist outside of Puerto Rico as well. So the recommendation in terms of management is that if you're trying to make effective environmental flow legislation, you should also consider the accountabilities of the agencies that are tasked with implementation. It may be, and it is likely, that still the misallocation of power and responsibilities, financial limitations, those are also playing a role, but it seems that accountability of state agencies could also be important to consider. Okay, moving right along. This one turned out particularly well. Okay, last question. Still going. Okay, so the last question is asking, how do management actions affect social and ecological resilience? And so we see here, again, people interacting directly with the water in Puerto Rico. It's a very popular swimming spot. So circling back to our idea of these water systems or social ecological systems, and knowing that water is variable through time and space, we can think about how these ecological and social systems have adapted to this variability. So one thing that's been suggested is this migratory life history of these different species that exist in the ecological system is actually an adaptation to this variability in water. So these animals can return to areas if there's low flow, and they can return to areas if it's too high of a flow. We also know that socially, people have built reservoirs to be able to hold water for these lower water scarcity events. And both these adaptations have worked fairly well for the past few decades. However, we know that because of climate change, they're expecting extreme climatic events that are going to increase on the island. And we've actually already seen this happening within the past few years. Hurricane Irma and Maria both hit within 2 weeks of each other in 2017, and they caused major devastation on the island. If you haven't seen a picture of Hurricane Maria hitting Puerto Rico, this is what it looked like. And then for droughts, again, 2 major droughts between 1993 to 1995 and 2015. So the question becomes, are these social ecological water systems going to be resilient to an increasing extreme events that are happening on the island? And so just like accountability in the resilience literature, you have to be very specific when you identify resilience. So for my purposes today, when I'm talking about the ecological system and the social system, I'm going to go over what resilience means for both of those. So in terms of the social system, I'm talking specifically about the water infrastructure system. There's a lot of things we could talk about in terms of a social system for water. I'm focusing on infrastructure. A resilient infrastructure system should be unlikely to fail and recover quickly. For my ecological part, again, today I'm talking specifically about stream ecosystems. And a resilient stream ecosystem should have functions that persist and bounce back after a disturbance. And so if we can think about these two as separate things, infrastructure and ecological as separate, but I want to combine them and think about water social ecological systems. And so a resilient water social ecological system would withstand risks and adapt or transform to new stream flows, generally. So we see if we are able to have a resilient social ecological system, we'd be able to adapt and transform with different stream flows. So in order to look at this question, today I'm going to talk about some of the methods I did for my dissertation, but not all of them. So the first thing we needed to do is to understand how this system is functioning. So what are the different components that are making up our social ecological system? So I constructed a baseline schematic of how the water social ecological system works, and we'll be going over that today, of how everything's connected. We also know that there have been water management actions that have been taken to try to increase the social system's resilience to drought. So how can they maintain water when there's not a lot of water available? And so what I'm going to do today is map 2 of these water management actions onto our existing water social ecological system to see how that actually interplays and interacts with resilience within the system, briefly today, in the few moments that we have left. Okay, so this is the big picture. I'm not going to go all over all of this, but we see we have many links between our social and ecological systems, both within social and ecological systems and across the systems. And so generally, we have the social system on the left, ecological system on the right, and in orange, we have these intermediate outcomes that are important for both the social system and the ecological system. So in the social system, we have available water, and then we have user demand. And you can think of this as meeting user demand for fresh water. In the ecological system, stream flow is important, as is these migratory aquatic animal dynamics, and then also water quality. And these links that I've created are based on peer-reviewed literature, so what's been researched in Puerto Rico, and then also an understanding of how the water infrastructure and delivery system functions in Puerto Rico. So we can think about, I'm going to simplify it to this sort of simplified schematic. But I think it makes more sense to think about how these different things are connected if we actually have a disturbance come into the system. So first we're going to think about how drought interacts specifically with the ecological system. So when you have a drought occur in Puerto Rico, we see lowered precipitation, lowered stream flow, lowered connectivity, which can influence migratory aquatic animal dynamics, these are the animals that are breaking down the algae, breaking down leaf litter, and that can eventually have effects on water quality. So we're seeing that when a drought happens, there's a reduction in stream flow, and that reduces water quality, just on the ecological side. There may be other things that are happening within the system, but we're just focusing on this today. In the social system, if we have a drought, again, we see reduced stream flow, but now we can think about that as there's less water storage that's occurring. There's less water flowing into these reservoir systems, which means that you have less treated water, less available water, and then that means there's eventually the potential for not meeting user demand. Sometimes we even see rationing on the island of Puerto Rico because there's not enough water to meet user demand. So this is what we see when we have a drought occurring. Now we can also think about hurricanes because we have another hurricane event that can also cause some of our system to respond in different ways. So yeah, reduced stream flow, reduced available water, and unable to meet water user demand. So if we have a hurricane coming into our ecological system, now we see increased precipitation, which can cause erosion, which means the more sediment within streams. But if we're just focused on the ecological system, this shouldn't be an issue because we have high stream flow, high connectivity, and sediment accumulation doesn't occur because the sediment's getting kicked out to the ocean. And we do see some minor migratory aquatic animal dynamics, but they respond quickly after a hurricane. Within a few weeks, you see these populations rebounding to pre-hurricane levels. If we shift and think about, and so increased erosion, increased stream flow, no sediment accumulation. If we think about hurricanes coming into the social side of the water supply system, focusing only on one pathway, which is wind, we see that wind, if we have high winds associated with a hurricane, you lose the electrical system, which means that you are affecting the ability to treat water and then also the ability to get water to high elevation users. These water treatment plants are typically on the coast. Then you have to pump your water back uphill. If you don't have electricity, these high elevation users don't have water. They're losers, they're water losers, and you can't meet user demand. So we see that it's really, during a hurricane, the biggest impact in terms of water supply is coming more from the electrical supply system. If you don't have electricity, then we're not being able to meet user demand and there's less available water. That's one thing to note. So now that we understand a little bit of how these disturbances occur within a system, and we have a little summary, I wanted to think, looking at our whole system, what happens when managers start putting more reservoirs on the island? This is a management action that has occurred and it has been suggested. In order to be able to have water available for the social system, you should add more reservoirs. If you add reservoirs, what you're doing is you're adding an intake or a barrier to be able to hold on to that water. But what happens to the system if we have this occurring? So focusing first on a hurricane coming in, so we're just going to go through the important links. If you have a hurricane coming, again, more precipitation and more erosion, but now when this sediment hits an intake or a barrier, it's going to stay in the system. The sediment will accumulate, it can have implications for water quality, and then you're also going to lose a little bit of your treated water as well. So your treated water it's going to be more damaged because we have sediment that's staying within the system. So within a hurricane happening, we have the sediment that's accumulating, and then that has implications for when you have a drought. So if you have a drought come in, all of that sediment that's been accumulated is actually reducing the amount of water storage that you have available. And so again, this will have implications for available water and then user demand. So even though you thought that building a reservoir was a good idea, after the hurricane comes, we've lost water storage. Also, because this action is coming in at the top, we're not doing anything about this system loss. You're still losing water as it's moving from treated down to available water as well. Now, if we think about repairing leaks, we can see that if you tried to fix the infrastructure, that would come into the system here, where you're maintaining available water. So you'd just be using the water that you have more efficiently. So now what we can see is that when a hurricane comes in, the ecological system can respond as it would without additional intakes or barriers on there. So we don't really see an ecological effect if we focus more on this management action. Likewise, if you have a drought, again, we don't see really any effect coming in from lower down. And actually what you would see is that you're reducing the system loss. So even though you're in a drought, you would be able to maintain the amount of water you have in the system and limit this system loss by focusing more on leaks. So what we see is that there are social ecological feedbacks that are influencing system resilience. Management actions with minimal ecological interactions, like repairing leaks, would actually increase overall resilience because we didn't see effects in the ecological system, just benefits in the social system. And so the recommendation would be that managers considering actions to increase social resilience to drought should consider feedbacks across the entire social ecological system, not just focus specifically on the social action to increase water availability. One more meme. Okay, so circling back, these were the 4 questions that I was interested in. Hopefully you feel like I've answered them, and I would say that this is my one takeaway for each chapter, and I'll leave this slide up when I'm finished in a moment. But since we're short on time, I just wanted to thank my committee for being amazing and supportive and patient as I learn all these definitions and try to apply them within my own system. Thank the Pringle Lab, current and past presents. Thank you all, lab sisters, for coming out to support me. All the administrative help, Odom and Icon have been amazing and supportive throughout this whole process. Multiple people have helped with data analysis, especially electricized Tom Preble, who's here today, for helping me figure out how these intakes interact within the water system. And the Department of Natural and Environmental Resources, who let me hang out with them for a summer. There's a picture of us at the top, and all the funding sources as well. These are the old Pringle Labs. I've been here a long time. There's been a lot of turnover. You might not recognize a lot of them anymore. Thank you all to friends for all the fun activities we've done. A lot of running, a lot of yoga, a lot of fun times. Work-life balance is important, so had a lot of that. And thank you to my family for coming and listening to me talk. Sorry that I forced you to do that. With that, I will again leave up my take-home things that I think were important, and I will take questions if there's any time.
Questions?
Great. Talk too fast. One more time. Yes, Mara?
I have a question about the fixing the infrastructure versus the reservoirs.
Mm-hmm.
What do you think are the major barriers to fixing the infrastructure versus putting in reservoirs? Is it more of a political thing, or is it a cost thing, or what would be the, trade-offs of that?
Yes, great question. So I can see the trade-offs as partly being political, like I saw in my thinking about legislation implementation. This is an issue where politicians like to do big flashy things like build a new reservoir, and fixing leaks is a little bit less sexy than building a new reservoir. And we see this in the US as well. It's hard to fix leaky infrastructure. So I'd say partly that. Also, it's been identified as hard to find these leaks within the infrastructure system, and they tend to break a few weeks after fixing the leaky infrastructure. So there's a lot of different components to that. But
can you talk about the fees? Because that was
yes.
a quote that you didn't bring in, and I thought it was one of the most.
The fees for fixing?
The political limitations on being able to kind of have the system be self-financing.
Yeah, and there's also this issue of going back to the governor and reporting to the governor. The water utility company is supposed to finance their own actions, but they're not allowed to raise the water fees because the governor doesn't think that reflects poorly on the governor. And it's true that if you ask people, they understand that the governor has a say in how water rates increase. So you can't increase water rates to finance better infrastructure because it looks bad politically. That's sort of been changing a little bit now, especially because Puerto Rico is in such a financial state that it is in, but it is hard to finance as well within the company. Yes, Kate?
I have a question about one I don't remember if it was the first or second chapter, so
Okay.
I apologize. But in one of the models, I think it was the first, used time as a proxy for number of intakes. Why didn't you just use intakes?
It's because we were doing it on a monthly time step, and the number of intakes didn't change fast enough. Like, you might go a decade and then have one intake come on. So it was just that the time scales were a little off. But in general, over the 37-year time period, more intakes were coming on through time. Yeah. Hopefully that answered. Yes.
There was a big article in the AJC today all about how dams in the U.S. are unassessed holistically. They're different by state. It's very subjective.
Mm-hmm.
Do you think that your habitat connectivity metric could be a standardized thing applied to all dams? And are there other ecological metrics that could better assess them?
That's a great question. Yes, so the connectivity index, there are multiple. Typically, when you're calculating it, you're looking at one species. So there are connectivity indices within the U.S. that look at how movement is affected for other species besides shrimp. But yeah, people are looking at that, and you can look at that as an ecological effect of dams. And you can actually calculate and simulate if you remove one dam, how would that affect connectivity versus another dam. But yeah, this issue exists all over the U.S. Yes.
The shrimps definitely seem to influence water quality and provide some sort of service, but the word ecosystem service never appeared in the discussion. Was it a conscious decision?
Ecosystem in any of it?
Yeah.
Yeah, so we know that these shrimp do provide ecosystem services, and so thinking about their presence as a proxy, but I didn't necessarily exactly evaluate the ecosystem services that are specifically being provided for shrimp, partly because we know how important they are. But maintaining them is a proxy for maintaining those services too. Great question. Everyone looks so tired. Sorry, one more.
I have another one.
Okay.
So the point about the organism's ability to rebound so quickly, I was really surprised that they could do that with the hurricanes.
Mm-hmm.
How? What allows them? What's their buffer?
So this research is being done in headwater streams, and so either the stream flow isn't high enough to blast these organisms out, or they're kind of hiding in refuge and able to climb quickly back. And specifically, it's looking at shrimp recovery, but also the ability to have this migratory life cycle allows these animals to recruit because they can come as larvae from all over the island. Within a few months, you should have these populations returning as long as there's no structures blocking their movement. Great question. Yes, Kathy?
You didn't mention anything about the backdrop of the fact that this is getting a lot of rainfall in El Yunque Forest, 4 meters of rainfall per year, and the dire financial situation of the whole island. Those are two things that I thought were interesting and you didn't touch on.
Yes, so we do know that typically El Yunque and Puerto Rico as a whole has been very wet, but climate predictions show that drier periods will actually get drier and hurricanes will be more intense. So we have kind of this polar opposite effect happening where you have dry season. And along with that, it is tricky that there are financial constraints on the island. That was part of the reason looking at whether altering this withdrawal rate would be able to sort of conserve these species if we know that removing dams probably isn't possible given the financial constraints. So it's kind of an idea of thinking how can we sort of meet these conservation needs with the least amount of money possible.
And might there be less withdrawal now that people are leaving the island because the infrastructure is so poor?
Yes, that should be possible that with less people present on the island, there should be less water demand as well. You can fix those leaks too. Yes, Akanksha. It's okay. I feel bad for everybody that needs to leave.
So I'm curious whether people think that the shrimp are an indicator species for the ecosystems there, and if they do think that, then maybe considering this context of connectivity for the different species that you looked at, maybe considering an indicator that's more sensitive compared to the shrimp might be something that, have people explore that.
So we had never really thought about connectivity for these other species. We knew that they did rely on a connection, but no one had really tried to quantify it within Puerto Rico before. So we actually thought it'd be the reverse, that shrimp would be much more resilient to these water losses, because we've seen that as you remove more and more water, these populations stay stable. And so the idea was to ask whether these other species also have that same response. So I think I would maybe say that they're probably the species most likely to return with just minimal amounts of withdrawal. And it's probably these other species like American eel that should be more of an indicator, since they're more sensitive to barriers within the system. Yes, John? Yeah, it's okay.
I guess with like the resilience of shrimp, and kind of touched on this a little bit, but how does their life history and kind of the sensitivity of their populations to different vital rates impact their resilience? It seems like the most important thing is that they all get out in the ocean, produce a bunch of young, and then those young normally die a lot anyway, and so trying to get up the stream really, even if there's like a 20% loss because of the barrier thing, it doesn't really matter. Like, what do you say about that?
That's a great question. Yeah, so we do know these individuals can produce like thousands of larvae, and they can live for, I believe Alan Kovich has seen some live for up to a decade. So once they get up into the streams and they can reduce larvae, as long as they can reach the ocean, it should make their population pretty resilient. We don't exactly know what it means to have a 20% less larvae versus 30% larvae, but because of this connection of all of these shrimp populations across the island, and there's also evidence that they're genetically connected across the Caribbean, and we're just thinking that the more larvae, the better, especially given that in some of these areas we have these high dams that have completely disconnected shrimp habitat, and they haven't been able to reach that for years. So thinking about this section of Puerto Rico as a potential larval supply, because there is at least partial connectivity, and we think they could be important for maintaining populations around the Caribbean Sea. Hopefully that answered your question. Okay.
Thank you.
Yeah. Thanks.